Okay, so I made a mistake last time, and sorry, not a mistake. I mean, I was going to tell you about the weight system of the Conway polynomial, and I forgot to do it, and that invalidated one of the homework questions. And it's also an omission, because it's kind of fun and good to know. So let me show you how to compute the weight system of the Conway polynomial, and it's really, really easy. So let me remind you that the Conway polynomial is defined by, sorry, I need a bit more space. So the Conway polynomial of, okay, sorry, I'm sorry, I'm having issues. So the Conway polynomial is an invariant of links, so not just knots, but also many component links, with values in polynomials in a variable called z with integer coefficients. So it comes out a lovely symbol, so z of z, right? But these are different z's. And it is defined by two properties. So first of all, the Conway polynomial of a k component unlink is equal to 1 if k is equal to 1 and 0 otherwise. So I could write it as the Kronecker delta function of k and 1. And second, the Conway polynomial of an overcrossing minus the Conway polynomial of an undercrossing is equal to z times the Conway polynomial, sorry, z times the Conway polynomial of the things that you get by replacing this crossing or undercrossing by a smoothing. And by the way, I had to use links because generally speaking, or not generally speaking, always, when you switch from a crossing to a smoothing, the number of components changes. So it has to be a link. Anyway, the claim was that the Conway polynomial is a finite type invariant, or more precisely, it's a series of finite type invariants. So if we write the Conway polynomial of a knot k as a power series, so sum m goes from 0 to infinity of Cm of k times z to the m. So Cm is just the mth coefficient of the Conway polynomial. So I write it as an infinite series, but it's really finite for every specific knot. Okay? Then the claim is that this Cm is of type m. Well, if it's of type m, then corresponding to it, there should be a map WCM. Sorry, m was a subscript. Sorry. So there is a map WCM, which is a map from chord diagrams of degree m modulo 4T relations and framing independence into the base abelian group, which in our case, so the coefficient is in z, so this goes into z. Okay? And my question is, what is this map? Or let's figure out what is this map. So to do that, let me remind you how we knew that the Conway polynomial was of type m. So basically, we needed to evaluate the Conway polynomial of a knot with m plus 1 double points. And each double point is resolved to an overcrossing minus an undercrossing. So in fact, this equality can be continued to the left to be, this is C of a double point. So, and then if you have m plus 1 or more than m double points, then you have more than m such differences. You get z to the power more than m. And if you get z to the power more than m, then the coefficient of z to the m is 0. Which means that Cm of a knot with more than m double points is 0. Which means that Cm is of type m. But now I want to know what is WCM on what is WCM? WCM is really the invariant, it's really Cm restricted to knots with precisely m double points. Okay? So I want to know what is so you know, let me write it this way. So WCM evaluated on some chord diagram with m chords. So I mean, I didn't mean the specific placements of chords. I just wanted to write a symbol for a chord diagram, and I wanted to say it has m chords. They could be placed differently, right? So this is by definition Cm evaluated. So let's give this diagram a name. So let's call this diagram D. So this is by definition Cm evaluated on a knot K, which represents the diagram D. So K is an M singular knot whose M singularities are arranged like these chord diagrams, whose underlying chord diagram is D. Okay? But what is this? So this is, again, using recursively, or using repeatedly the definition of the Conway polynomial. This is going to be z to the m, or this is going to be, so you know, let me write it this way. It's the coefficient. So Cm is the coefficient of z to the m. So it's the coefficient of z to the m in the Conway polynomial of Kd. So in the Conway polynomial of Kd. But the Conway polynomial of Kd is using the recursive formula, the skein relation. It's the Conway polynomial of the knot that you get. So if you take Kd and in it you replace every place you see a double point by a smoothing, right? Sorry, sorry, I forgot a crucial term. So the crucial term is, well, every time you replace a double point by a smoothing, you get a factor of z. So I forgot here the crucial factor of z to the m times this. Okay? But now, the coefficient of z to the m inside this, okay, is the coefficient of z to the 0 right? It's the coefficient of z to the 0, the coefficient of z to the 0 inside, well, just don't put the z to the m. So inside the Conway polynomial of kd, in which you replace every double point by a smoothing. But the coefficient of z to the 0 is just a different name for C0. So it's C0 of KD, in which you replace every double point by a smoothing. Okay? But now I claim the following. So if you look back at the Conway polynomial, so suppose you have, suppose I want to compute C0, so the coefficient of z to the 0 of a knot that has sorry, not a knot, a link that has k components. Okay? So I can do it by flipping crossings until all the components are apart from each other. And then I'll get the answer written here. But I have to pay a price. The price is that every time I flip a crossing, I have to pay a price z times c of a smoothing. But I'm looking at C0. I'm looking at the coefficient of z to the 0. So a price which is multiplied by z doesn't affect C0. So the conclusion is, so these two things taken together imply that C0 of a k component link, no matter what, I mean, here I wrote the unlink, but here I say any k component link is equal to delta k1. Okay? Again, because if you have a k component link, you start flipping crossings. Flipping crossing costs at no cost at the level of the constant term, because the cost is always multiplied by z. And so you go back to, you end up getting to the unlink, and for the unlink you get delta k1. So taking this down to where we need it, we find that this is equal to 1 if kd subject to the replacement has one component, so is connected, and 0 otherwise. Okay? But I claim that you can see it. Okay, so you know what, so this was really the weight system of the mth coefficient of the Conway polynomial evaluated on a diagram D. It's given by this. But to compute this, you don't even need to know what is KD. You can compute it directly from the diagram. Namely, if you have, so let's figure out what does this replacement mean at the level of the diagram. So suppose you have a chord in a diagram. So let me just draw it as a, so here is the circle parameterizing the knot, and here is one chord inside a chord diagram. How would I realize it or how would I find a knot whose underlying chord diagram is this? Well, I would do the following. I would, I think we've done it. I would draw a knot that looks like this. Okay, so I created a double point exactly where the chord used to be on the parameter space. Okay? But now if I apply to this, so this is how I go from D to a knot representing D. I replace every chord by a picture like this. Okay? But now, if within this picture I do the second operation, namely I replace a double point by a smoothing, then this is maybe a bit hard to see the way I drew it. Let me see if I can see it. So this is oriented going up, and then I do the smoothing, and it gets to go to the through here. So I get this picture, and if I enter from here, I end up doing a silly kink and come out this way, right? But we're going to compute C0 of this. And C0 is insensitive to knotting, only to the number of components. So this is equivalent, in as much as C0 is concerned, to this picture. Okay? So what I did is I ended up replacing the chord by a bridge. Right? So now let's use it for an actual computation. So what is the weight system of Conway, of the second coefficient of the Conway polynomial, evaluated on, let's say, this chord diagram? So the rule is you end up, all the replacements, replace the chord by a bridge, so each chord by a bridge, so you'll get a picture like this. This picture has 3 connected components, but the rule was if you have 1 connected component, you get 1, and otherwise you get 0. This is not 1, so you get 0. On the other hand, if you apply the WC2 to this chord diagram, well, again, you end up replacing each chord by a bridge, so you get a picture that looks like this: 4 intervals and 2 bridges. If you look at this picture, it actually has only 1 connected component. So WC2 maps it to 1. Okay? So having computed the weight system of the Conway polynomial, by the way, and the computation is, so you know what? Let's now do it for a chord diagram with 4 chords. Let's say, let's do it the hardest one. So the fully mixed chord diagram. Okay. So in principle, I need to do this to do this replacement, but I can do it in a much faster way. I can just start walking and just remember that every chord becomes a bridge. So I'm going to walk on the left side of the bridge. It's going to get me out here. I'm going to continue walking. I'm walking on the left side of that bridge. I'm going to continue walking. I'm going to walk on this bridge. then I'm going to continue walking, I'm going to walk on that bridge, I'm going to continue, now I'm going on the other side of a bridge I visited before, I keep going like this, and by the time I'm done, I've visited everywhere. So it's one connected component. So the conclusion is that the weight system of the fourth coefficient of the Conway polynomial maps this to 1. And I don't know, let's do another example just for fun. So suppose I want to compute the Conway weight system on this chord diagram. So, I could start doing the same, but you know what, let me do the same. So, I follow, basically I never cross the chords, and I came back to the beginning without visiting everywhere else. So this will have at least 2 connected components. In fact, it will have 3, right? Because a second connected component will be this one, and the third one will be that one. And anyway, this implies that this goes to 0 by WC4. Okay, so now that I've computed the weight system of the Conway polynomial, let's check if it satisfies the framing independence relation and the 4T relation. Okay? Yes?
Yeah, just a quick question.
Excellent. You should ask a lot of questions because it allows me to drink tea.
The C, does it mean that all M-type diagrams are of C0, say of type 0? Maybe I'm not asking the question well, I'm just kind of confused. So when you are computing the weight system of a chord diagram of the Conway polynomial, you are replacing Cm by C0.
But, well, I'm doing a sequence of replacements, right? I first of all replace every chord by a double point. Then every double point becomes Z times smoothing. But since I have m of them, I get Z to the m. And then since I'm looking at the coefficient of Z to the m, that's the same as looking at the coefficient of Z to the 0 in the result. Okay? Okay.
So we're actually getting an understanding of how the Conway polynomial loses information between knots, and we can even cook up using this idea you're saying, 2 knots with the same Conway polynomial by just putting together different chord diagrams and trying to...
No, I don't know how to, I don't know how to get 2 knots with the same Conway polynomial out of this. I genuinely don't know. Sorry, I'm not sure what your logic was, but me personally, I genuinely don't know how to do it.
Oh, I was vaguely guessing because you take one chord diagram and then you, okay, maybe I just think about it a bit more. I thought this was something that happened with a bit of work, but yeah.
Okay, good. Anyway, so I need to check that this, or I don't need to check, but it will be a good sanity check to check whether this satisfies the framing independence relation and the 4-term relation. So the framing independence relation said that if you had an isolated chord, you get 0. But if you have an isolated chord, you have an isolated loop, which doesn't go through everything. So you have more than one connected component, so clearly you get 0. Okay? And what about the 4T relation? So the 4T relation, so now I have to draw it. So the 4T relation says this minus this is equal to that minus that. All of them have a chord in the same place, and another chord that trades places. Okay, And now let's do the same process. So here, I'll have one path that looks like this, another path that looks like this, and then it continues. And in fact, I don't know how it continues because there are more chords that I'm not drawing. So I'm only drawing the neighborhood of the chords that I know of, okay? And another path that continues that goes like this. But this is exactly the same as here. So here I have this, I have that, and I have that, and these two are topologically the same. In other words, when I enter the known part from here, I exit here, same as here. Right? So basically the known part of the universe, maybe I should have drawn it without the extra edges. So the known part of the universe is made of 3 arcs. Right? And then there is more. And the 3 arcs are connected by 2 chords. And then I ask myself, suppose I travel through the diagram, what will my trip through the known part look like? And here, the trip looks like, okay, here, if I enter from here, I exit the known part from here. If I enter from down here, I exit the known part from here. And if I enter from here, I exit the known part from up here. Okay? And that's exactly the same as what happens here. So these two get the same value, and these two get the same value. Let's check it. So if I enter the known part from here, I exit here. This is the same as here. If I enter from here, I exit in the same place. I mean, the path was more complicated, but it ended up doing the same. And if I enter from here, I exit here. If I enter from here, I do something more complicated but exit in the same place. And likewise for the remaining, the remaining part is trivial. This and that. So we verified 40. Okay? Good. Okay, so now back to where so this was what was supposed to happen earlier and I forgot. And back to where we were before. So I wanted to prove to you 2 propositions, and I decided that I don't want to prove them, but only indicate how the proof works. Okay? So proposition number 1 said that if invariant number 1 is of type M1 and invariant number 2 is of type M2, then their pointwise product, then V1 times V2 is of type which is the same, the sum. And the second proposition says the following. So the claim is that there exists, there exists a unique operation delta going from A into A tensor A, such that the weight system of the product can be computed from the weight system of these two using this operation. Precisely such that the weight system of V1 times V2 is equal to this operation box fed into the weight system of V1 on the first tensor factor times the weight system of V2 on the second tensor factor. Okay? So I don't want to prove these 2 propositions, but I want to tell you what the operation delta is and well, why do you expect it? And then the proof is basically to convert my words into formalities. Okay? So, okay. First of all, we expect this proposition because finite type invariants are like polynomials. So if you have a polynomial of degree m and a polynomial of degree, a polynomial of degree m1 and a polynomial of degree m2, the product is of degree m1 plus m2. Now, how do you see it for polynomials? So suppose I define polynomials using derivatives, then how do I see it for polynomials? The answer is that it's a fancy application of Leibniz's rule. So suppose I have a polynomial like, let me do something really easy because again, I just want to see how it works. So suppose I have a polynomial like x cubed and another one x to the 4, and I want to prove to you that this is something of degree 7. Okay? So how do I do it? I apply to it 8 differentiation. 1, 2, 3, 4, 5, 6, 7, 8. Okay? And Leibniz's rule says that when you differentiate a product, the differentiation chooses which of the two factors to differentiate. And you sum over all choices, right? I mean, do I remember right? Is this Leibniz's rule? F times g prime is f prime g plus f g prime. So really, you copy the fg and the prime gets to choose if it goes on the f or on the g. And you sum over all the possibilities, right? So, the first differentiation gets to choose if it goes on the x cubed or on the x to the 4th. So this one gets to choose, let's say it chooses this one. I have to sum over all possibilities, I'm just looking at a typical summand. The second differentiation gets to choose whether to act on what remains on the x cubed or on the x to the 4th. Let's say it also chose the x cubed. The next differentiation maybe chose this one, the next differentiation maybe chose this one, the next differentiation maybe chose this one. But at the end, I have 8 differentiation to distribute between something of degree 3 and something of degree 4. Right? So either I'll have more than 3 differentiations here or more than 4 differentiations here. Right? Because if I had less than 3 here and less than 4 here, I wouldn't have 8. I would have at most 7. Okay? So I will end up applying too much differentiations to either this factor or that factor, and in either case you get 0. Okay? So I just proved to you that x cubed times x to the 4th is a polynomial of degree 7. I am sure you are excited. But
we
now...
only know it's a polynomial of degree at most 7. Right?
I stand corrected. Thank you, Jesse. Now, in fact, I was sitting corrected. Now I'm standing corrected. But now suppose I wanted to compute the weight system. To compute the weight system means that I apply exactly the right number of differentiations. So I take my x, let me reduce degrees. So I take my x squared times x cubed and I apply to it exactly 5 differentiations. And then the only way I'll get a contribution, you know what, let's not call it x cubed and x squared and x cubed. Let's make it a general polynomial. So f and g. But here the degree of f is equal to 2 and the degree of g is equal to 3. Now, the only way I will get a contribution to the answer is if the two if the 5 differentiations will be split 2 on F and 3 on G. Right? So the answer will be the sum of all ways of splitting the 5 times differentiation into 2 to left and 3 to right. Okay? And then the 2 on the left will act on F, the 3 that go to the right will act on G, and we're done. Okay? Sorry, we're not done, but we now know how to compute. And I ran out of space, so I need to add a few pages. I'm sorry about that. Okay. So now let's do it for knots. Okay? So suppose I have V1, which is of type 2, and V2, which is of type 3, same as F and G, and I want to compute V1, or the weight system of V1 times V2, evaluated on a chord diagram which has 5 chords. I don't know, I'm not too fancy, so but let's, okay, I don't know, here is a chord diagram with 5 chords. Okay? Now, really, each chord corresponds to a double point. A double point is a differentiation. So each chord is really like a differentiation in the game we played before. So I have 5 differentiations, and I have to apply them to a polynomial of degree 2 plus 3, which is 5. Okay? So each differentiation should choose whether to go and act on V1 or on V2. And exactly 2 of them should choose to go to V1, and 3 of them should choose to go to V2. Okay? So the result is, so it's basically, well, it's a sum over splittings of, if I call this diagram D, so into left and right. So what do I mean by that? What does a splitting look like? So a splitting means that you mark some of the chords by left and some of the chord by right, and the number of chords that are marked left is equal to the degree of V1. So I must have 2 chords marked left, so let's say it's this one, and all the rest are marked right. And then the splitting is, so this becomes a pair of chord diagrams, and the first one is made out of the chords that went to the left, and the second one is made out of the chords that went to the right. So I have to look at the sum of all such splittings. And for each such splitting, so each such splitting is again a differential operator, and so maybe I should give them a name. So this is DL and this is DR, and I have to apply W, the weight system of V1 to DL, and the weight system of V2 to dr. Okay? Again, I just copied. I copied the formula from calculus only verbatim, almost verbatim, without. This is the only interpretation I can have of that formula. Okay, I haven't formally proven it, but this seems reasonable. But anyway, this inspires the definition of the map delta. So the map delta is a map from A into A into A tensor A, and it's the map which maps every diagram to the sum of all ways of splitting it. So it will map, let's say, a 3-chord diagram, this one, into basically the sum over all ways of marking this diagram with left and right, and then splitting accordingly. So the left ones go to the left tensor, the right ones go to the right. Is it clear? So basically, you know, if you want to compute delta of a chord diagram, you write two circles and you sum over all ways of deciding which chords go to the left and which chords go to the right. Okay? And now the formula that I suggested is essentially proven. So the formula W V1 times V2 of D is equal to this delta followed by W V1 multiplied by W V2 was essentially the formula that was written above. If you have a diagram, using it to differentiate V1 times V2 is the same as sum over all ways of splitting it and feeding it and then either differentiating V1 or differentiating V2. But if you split it incorrectly, you get 0. So you end up only splitting, so right, if you split it so that not the right number of chords are fed into WV1, you get 0. So, so in effect, you're only summing over the splittings that I mentioned here, namely the splitting in which 2 goes to the left and 3 goes to the right. Okay? And now I have a number of claims to prove. Okay? So first of all, claims, well, okay, first claim is that this is actually right. You know, I mean, I kind of told you how I inspired to get to it, but the claim is that you can actually prove it if you're very, very careful and you write all the details. So, one, this is right. But you know, there is a sanity check to make. So, the way I defined it on chord diagrams. You have to check that it descends to the quotient by the 4t and the fi relations. So really delta is defined on diagrams with values in diagrams times diagrams, but I claim that it descends mod 4t to an operation also called delta going from A into A tensor A. Maybe I will not prove it, but it's worth proving. Okay? And finally the theorem. So theorem. So if you look at the space A, and we have already endowed it with a product M. we have just endowed it with another operation, delta, going from A to A tensor A. In fact, it has two more operations that maybe I'll mention in a moment, but probably I'll run out of time, so I'll just mention that they exist and they're not terribly interesting. Epsilon and eta, and this one is called the, this one is called the unit, and this one is called the co-unit, and these are like the operations that turn an algebra to an algebra with a unit, and a co-algebra to a co-algebra with a co-unit. Okay? So the claim is that this is what I said at the beginning. So is a connected, graded, commutative, and co-commutative by algebra. So what do I need to show? So I need to explain what are epsilon and eta, and maybe I'll do it later, but these are the minor things, right? This is just the units, okay? But the bigger things are, I need to convince you that M and delta are associative and co-associative and commutative and co-commutative. Well, for M I've done it already. For delta, so why is delta commutative or co-commutative? Well, it's kind of obvious. I mean, if delta is the sum of all splittings, clearly, you know, you just have to flip the L's and the R's and you got the opposite splitting. I need to show you that delta followed by box followed by one tensor box is the same as box followed by box tensor 1, right? This is the co-associativity. But again, this is obvious. If you have a diagram and you split it into left and right, and then you split the rights into the left of the right and the right of the right. So right 1 and right 2. At the end, you've created all ways of splitting the diagram into three parts. A part that you will call left, a part that you will call middle, and a part that you will call right. Right? So if you want to split the diagram in three, there are two ways to do it. You either split it to left and right, and then split the right into middle and right, or you split it into left and right, and then split the left into left and middle. Okay? So this is easy, and the only thing that remains is to show the compatibility of delta and M. Okay? So the compatibility of delta and M is the following property. If you have two chord diagrams, so one and another one, I don't know, this one, then the claim is that multiplying and then applying the coproduct is the same as applying the coproduct and then multiplying. So splitting here and then combining is the same as combining and then splitting. And I don't have the time to make it precise because my alarm just beeped, but I claim that once you do it, it's completely easy. Okay? So the theorem is proven, and I'll have to tell you what to do with it later. Okay? So I'm sorry, I'm out of time, but see you on Friday. Questions, comments before I shut down the video? Okay.